Welcome everyone to today's deep dive into the world of tanks, the heavily armored giants that have reshaped the art of warfare across decades. In this in-depth video, we will peel back the layers of technical innovation and strategic evolution that define these feats of engineering. Tanks are not merely vehicles. They are mobile fortresses combining advanced metallurgy, state-of-the-art weapon systems, and pioneering propulsion technology. With roots stretching back to the trenches of World War I, tanks have continually adapted through rigorous design iterations and battlefield requirements. Today, we aim to explore sophisticated concepts behind tank mechanics, historical milestones, and the fascinating interplay of engineering and military strategy that resonates even with modern combat scenarios. Our discussion is intended for experts and enthusiasts alike, bridging historical insights with cutting-edge technical analysis. Throughout this video, we will delve into the precise engineering details of armor composition, the evolution of firepower, and advancements in mobility mechanics that have transformed tank operations over time. We will assess how factors such as alloy development, computational design, and innovative energy management systems have been harnessed to create machines capable of multifaceted combat roles. Whether you are an engineer, a military historian, or simply a fan of mechanized warfare, this exploration promises a thorough examination of the technical intricacies behind these commanding war machines. So buckle up and prepare to engage with a content-packed exploration that balances numerical data, system-level analysis, and a friendly yet precise examination of the deep technical signals underlying every tank's design and deployment strategy. Let's launch into the robust historical analysis and advanced technical breakdown that these armored titans command on the modern battlefield. Stay tuned as we unravel the complexities and celebrate the ingenuity that continues to inspire modern military engineers around the world. Absolutely. Let's get started now. History of tanks is a fascinating journey, marked by rapid innovation and profound transformations in military doctrine. The inception of tanks dates back to World War I, when the static trench warfare demanded a breakthrough against entrenched defenses. Early designs, such as the British Mark I, emerged as reactive solutions to the limitations of infantry and artillery. These initial tanks, albeit rudimentary in design, were instrumental in blunting enemy machine gun nests and breaking through fortified lines. Although plagued by mechanical unreliability and awkward maneuverability, these pioneering machines set the stage for continuous experimental developments. In the interwar period, tank development took on a new dimension. Engineers and military strategists collaborated closely, exploring not only basic mobile fortification, but also complex tactical roles. This era saw significant advancements in chassis design, powertrain scalability, and armor composition. Noteworthy is the influence of European mechanization theories, particularly those from Germany and the Soviet Union, which experimented with different doctrines of combined arms warfare. The drive to achieve a balance between mobility, protection, and firepower led to iterative improvements that mathematically redefined battlefield performance metrics. Precise data analysis and weight-to-power ratios began to play an essential role in design enhancements. World War II marked a watershed moment for tank technology. Battles such as Kursk and El Alamein underscored the potential of armored units in orchestrated high-tempo operations. Tanks not only offered a platform for direct assault, but also served as mobile command centers and artillery platforms. The integration of superior fire control systems, advancements in gun stabilization, and evolving turret designs transformed tanks into versatile assets capable of engaging targets at diverse ranges. Statistical reports from wartime archives indicate a significant uptick in kill ratios and battlefield survival rates as tank technology matured. These historic milestones underscore how continual investments in research, rigorous testing, and cross-national knowledge sharing drove the evolution of tank warfare. The legacy of these early developments remains embedded in modern armored systems, as engineers and military tacticians continually refine design principles based on lessons learned in the crucible of war. Beyond these major historical moments, numerous lesser-known battles and experimental prototypes further enriched the narrative of tank evolution. Detailed analyses of captured enemy blueprints and reverse engineering efforts provided invaluable insights that informed subsequent design modifications. Nations invested heavily in research facilities and simulation labs to test performance characteristics under extreme conditions, ranging from desert heat to Arctic cold. These investments were driven by meticulous studies of material fatigue, armor penetration capabilities, and optimal fire control algorithms. Scholarly research and classified studies alike contributed to a multi-layered history. Tank design has continuously evolved, driven by relentless technological innovation and the desire to optimize battlefield performance. At the heart of early designs was a focus on basic mobility, with robust continuous tracks and simplistic yet effective suspension systems engineered to navigate rugged terrain. Advanced metallurgy played a crucial role. Early armored vehicles employed rolled steel plates, while subsequent iterations adopted hardened steel alloys and composite materials to improve durability and resistance to penetration. Detailed computational modeling and stress analysis allowed engineers to refine hull shapes and turret configurations for optimal weight distribution and improved ballistic protection. In parallel with armor improvements, the evolution of firepower was equally pronounced. Initial tank cannons were designed for direct frontal engagement, but modern tanks now incorporate versatile weapon systems capable of both direct fire and indirect artillery support. Advances in ammunition technology, including the use of armor-piercing, fin-stabilized discarding sabot, APFSDS rounds, and high-explosive anti-Tate warheads, have multiplied the offensive capabilities of these vehicles. Enhanced fire control systems, featuring laser rangefinders, thermal imaging, and computerized ballistic calculators, further enable precise targeting even at long ranges. Such innovations are supported by extensive field testing and data analytics, which continually inform iterative design improvements. Engineers have also given considerable attention to mobility enhancements. Innovations in engine efficiency, hybrid power systems, and improved transmission mechanics have allowed modern tanks to achieve higher operational speeds without sacrificing reliability. In-depth studies of weight-to-power ratios, traction controls, and differential systems have led to breakthroughs in maneuverability, making it possible for tanks to execute rapid tactical shifts under fire. Aerodynamics has emerged as an additional design factor. Contemporary tank models are streamlined to reduce air resistance, which in turn helps with both engine performance and fuel efficiency. An often overlooked aspect of tank evolution is the integration of modularity in design. This approach allows for the quick upgrading of systems, including engines, armor packages, and communication arrays, which is vital in an era where battlefield requirements change rapidly. The emphasis on modularity is supported by advanced manufacturing techniques such as 3D printing and computer numerical control, CNC machining, enabling precise customization and rapid prototyping of components. Extensive simulation-based testing complements these physical prototypes. Over the decades, iconic tank models have emerged as benchmarks for success. Legends such as the Soviet T-34, the American M1 Abrams, and the German Leopard 2 exemplify the fusion of robust design and sophisticated technology. Comparative performance metrics, including assessments of firepower efficiency, armor integrity, and mobility indices, are critically analyzed to chart the evolution of design philosophies. This continuous evolutionary process highlights a commitment to pushing the boundaries of what is technically possible, ensuring that tank design remains at the forefront of modern military engineering. Tanks have played a transformative role in warfare, emerging as pivotal instruments of military strategy across multiple conflicts. In historical battles, tanks often served as both shock troops and mobile fortresses, breaking enemy lines with sheer force and strategic surprise. Detailed analyses of engagements such as the Battle of Kursk reveal that tank formations, when coordinated with infantry and air support, can decisively alter the tide of combat. Modern warfare still sees tanks fulfilling a multifaceted role, wherein digital battlefield management systems and network-centric operations have expanded their tactical utility. Historically, tank battles such as the German counteroffensives of World War II demonstrated the destructive potential of massed armored units, with quantitative studies indicating kill ratios rising above 1:5 to 1 in balanced engagements. In contrast, Modern tanks benefit from real-time data integration and precision-guided munitions, factors that allow for adaptive battlefield strategies informed by live analytics. Advanced sensor suites and battlefield management systems now facilitate real-time targeting, enabling tanks to engage moving targets with unprecedented accuracy, a dynamic that previous generations could only theorize. Historically, tanks were often deployed en masse to maximize force concentration. Modern doctrine, however, emphasizes flexibility, precision, and the ability to operate in combined arms teams. Archival records from battles like El Alamein illustrate that effective armored maneuvers were often quantified by displacement speeds, with rates measured in meters per second serving as key performance indicators. Modern combat exercises often simulate complex urban environments and combined terrain challenges, where tanks must adapt to close-quarters combat and long-range suppression simultaneously. The integration of unmanned systems with traditional tanks has introduced a new era of combined operations, where autonomous drones and robotic support vehicles work in tandem with armored units. Experts note that today's tanks, bolstered by digital innovations, exhibit enhanced situational awareness through integrated systems that process multispectral data streams, allowing for statistically significant reductions in collateral damage. Comparative studies of Cold War-era tank battles with modern engagements reveal not only technological leaps in sensor and communication capabilities, but also a revolution in tactical doctrine that prioritizes agility and precision. Field data compiled from recent military exercises indicate a noteworthy improvement in engagement efficiency, with modern armored units achieving target neutralization rates that surpass historical averages by nearly 25%. These advancements highlight the ongoing evolution of armored warfare, where a blend of machine precision, real-time analytics, and adaptive tactics continues to redefine combat effectiveness in both conventional and asymmetric battlefields. Looking ahead, ongoing research and development projects are focusing on the integration of artificial intelligence in tactical decision-making, the miniaturization of advanced sensors, and the fusion of data from multiple platforms to create an even more cohesive and responsive armored force. The technology and mechanics underlying modern tanks represent a confluence of advanced engineering principles and cutting-edge digital integration. A tank's internal architecture is designed around compartmentalized systems that include propulsion, fire control, communication, and defensive modules. Modern propulsion systems leverage turbine engines, diesel engines, or hybrid variants, each optimized through computational fluid dynamics, CFD, simulations to achieve superior power-to-weight ratios. Fire control is driven by an intricate network of sensors, including thermal, infrared, and radar systems, which transmit data to centralized processors that compute firing solutions in real time. The integration of these sensors with machine vision and targeting algorithms allows tanks to accurately track moving targets and automatically adjust turret orientation. Cutting-edge communication systems, often based on secure satellite links and encrypted radio frequencies, ensure seamless interconnectivity between units and command centers. The defensive capabilities of tanks are augmented by active protection systems, APS, that employ radar detection and countermeasure projectiles to intercept incoming threats. Engineers meticulously simulate ballistic trajectories and armor penetration scenarios using finite element analysis, FEA, to refine armor layouts and material compositions. A remarkable feature in modern tank mechanics is the use of modular electronic controls that allow for quick system diagnostics and rapid replacement of faulty components during combat. The synchronization of propulsion, fire control, and defensive systems is achieved through integrated software platforms that facilitate real-time system monitoring and predictive maintenance. Data from onboard diagnostics are continuously analyzed using machine learning models, which predict maintenance needs and optimize resource allocation with impressive accuracy. In summary, the convergence of mechanical engineering, computational analysis, and digital communications has produced tanks that are as much about software optimization as they are about physical robustness. Each innovation is meticulously scrutinized through quantitative testing, ensuring that every component meets stringent safety and performance standards. In essence, the blend of robust mechanical design with sophisticated digital systems forms the backbone of modern tank engineering. Research advances yield platforms that are increasingly resilient, efficient, and adaptable today. Looking into the future, the evolution of tank technology promises to be as transformative as its storied past. Experts envision the integration of artificial intelligence for autonomous threat detection and decision-making. Tanks may soon operate with enhanced network connectivity, creating synergistic relationships with unmanned systems and other robotic support vehicles. Research into advanced materials, including metamaterials and nanocomposites, is expected to usher in a new generation of superior armor systems, offering both increased protection and reduced weight. Moreover, developments in energy storage and propulsion technologies could lead to hybrid or fully electric powertrains, transforming mobility and operational sustainability. Simultaneously, the future battlefield will demand even greater adaptability. Modular designs and rapid retrofitting capabilities will allow tanks to be upgraded swiftly in response to emerging threats and new technological paradigms. This flexibility is essential in an era where cyber and electronic warfare increasingly influence conventional combat. In conclusion, the journey of tank development, from rudimentary armored vehicles to today's technologically sophisticated machines, underscores a relentless pursuit of innovation. The legacy of past advancements fuels the promise of future breakthroughs that will transform the battlefield. Thank you for joining us on this technical deep dive into the world of tanks. Don't forget to like, subscribe, and comment below as we continue exploring the evolving landscape of armored warfare today.